Good evening. Welcome again. Today, the plan is, here's our class schedule. So we have a plan and then what we actually do. If we look at the class schedule on e-learning for each lecture, there's a planned topic to be covered. And the actual, I update this field right after the class to show what we actually did, okay? So last time was to work with Freescale CodeWarrior, then this is what we actually did. Today's class plan is to to work with CodeWarrior. We're going to start using CodeWarrior, right, for our first assembly program for HCS12, single step through it, see all the system registers and memory using CodeWarrior. Then we're going to download the program on the hardware and run it on the hardware. Okay, during which we'll be looking at the datasheet for the microcontroller unit. We didn't look at it before. This is for today's class, so to break the ice with the development environment. Then we're gonna start writing programs. We're gonna go concentrate on see those guys who come late. I don't see I don't know, I don't see their, am I sharing my screen?
No. I was about to say that.
Yeah, okay, play.
Are you sharing something? I will not see.
I'm not sharing. I'll share now. I was recording. Guys, who come late? I don't know. I didn't see. By chance, I looked at my phone. I found them in the waiting room. So try to come on time, please. Play. So this is what I was saying. In the class page, the class schedule here, I have a coverage plan for the 16 weeks, okay? A lecture by lecture, okay? However, sometimes what's planned is not what actually happens. Sometimes things shift between a lecture to another and something pop up, whatever. Today, so what, this is what I usually, this is the plan, then this is the actually cover, okay? Today, our plan is to work with CodeWarrior Development Studio, build and simulate programs, debug, run it on the computer and on the hardware, the microcontroller, monitor registers, memory, and everything, to prepare ourselves to start developing software, embedded software. Next class, and this is the plan for the coming 3 classes, yeah, next class and the coming week 6, whole week 6. It is about embedded software development. Next class, my plan is to go with you through embedded software design process from the idea until you get to the production deliverable, which is the executable code for a whole system. And then we're gonna look at the conventional ways in designing embedded software. Then I'm gonna cover model-based embedded software design, and then design verification and validation techniques. Then we go back to writing code, and we use these what we learned here, the ideas, how to design, plan for our programs before developing the actual program. Then we write code. We're going to go through writing embedded software code using assembly, then using C, then using model-based, and run them on the hardware. So this is a brief on what's coming next in the next few weeks. Okay. Last time we just started with CodeWarrior. Yani, I'm going to pretend that we didn't do anything. We're going to start everything from scratch. So to have this lecture as a standalone. I want to call it Starting with CodeWarrior and Writing Your First Assembly Program for HCS12. So the folder we created last time was class demo 1. I'm going to just delete it and build it again, okay? Well, I'm going to delete what's in it, the project, delete it, and start a new project again. So you go, of course, you downloaded CodeWarrior IDE from the link I provided in e-learning. It is free for education purposes. And I was reading something today mentioning that they put the Freescale, when it developed CodeWarrior and integrated something called Serial Monitor within it, and I'm going to talk about that later. The amount or the cost of developing such environment was meant there was no way that they were planning to get back cover their cost from selling or anything. So they said they gave it for everybody for free, and the purpose was to sell more chips, basically. Anyways, it's a very powerful tool. Right. Okay, so I'm not going to use this wizard. Just to remind you, you can go to File, New Project. Okay, New Project, or this will start the dialog I just closed. So New Project. When you open it, you find HCS12, HCS12X. So we're at HCS12D family, our HCS12. Then we find the 256 flash memory option, DG or DP. If you do find the DG, we found it last time, DG 256B. This is our family member. Next, then we said we're going to use absolute assembly. So we're going to write assembly code, and the addresses we provide are not relocatable, they're absolute. We're going to decide where we want to write everything. Okay, then we choose the place we're going to store our program. You create a folder, just put it there. And this was the folder we created last time. Give it a name, save it. The project file, the project is MCP type. Okay, extension. Next. Then if you have any files you want to add to the project, you've previously written C or assembly, you can add them. We don't want any device initializations. We do everything ourselves. Finish. And this is the first thing you get. On the left side, there is a tree showing your files. So the main.asm. .asm yani .assembly. This is an assembly file. If we choose the C option, we get a main.c. So then the includes. This assembly file includes the derivative. The derivative is the family member we mentioned. If you open it, it says include this dg256.include file. That's it. And the dg256 includes definitions of equate. This is something called equate is a derivative, directive, sorry, is a directive in assembly. Basically, you use it instead. For example, DDRB. This is a data direction register for port AB. It is addressed to in memory. So, and for example, DDRA, A and B, 2, yes. For DDRB is 3. DDR E is 9, okay? So a lot, any numbers, all numbers. Port E is 8. You don't want to remember all these numbers. So you have a file that has a word, okay? port E. You just use the word port E and it will be converted to a memory address. And when we started talking about HCS12, these are registers. We said that registers here, the non-CPU registers. I'm not talking about the CPU register, the accumulator, and other A, X, and Y index registers. We're talking about the other I/O and port registers. These are dealt with as memory addresses, and they're really located in the SRAM. Sorry, yes, in the SRAM, and mapped to the actual ports. They're given addresses. And you don't have to remember these numbers. The include file here just gives you an option to use the word. So port B, you just say port B. You don't need to remember that is address whatever. Okay. So let's go back to our main.asm. When you first build your first project, this is what you get. First, there should be a place to define your RAM variables. So when you write a C program, you say integer X, character Y, whatever. These things usually are in RAM. So you should have, you should be able to reserve memory locations in the RAM, in the volatile memory that you want to temporarily use. And there should be a place for the program that should be stored in the program memory, in the flash memory. Okay. In this case, they call it RAM start. RAM start, read only memory start. RAM here is the flash memory. Okay, not the E² RAM that is used for data. When I finish the first program, we're going to go check this family member, this microcontroller unit data sheet, and look at these addresses. Why is this program memory? Why does it start at address 4000 hex? Are there other options, or is it that way? So we're going to look at. To know these things, we need to look at the data sheet. When you first build your first program using the wizard, what you get is this. You get a program that is ready to run, that has a code to calculate the Fibonacci series. Okay. So we don't want to do that. You know the Fibonacci series, right? The 1, 1, then 1, 1 plus. You know it, right? Okay. Okay, since you're not answering, then you know it. I'm not going to say anything about it. طيب. So here's what you have. The RAM start. طبعا RAM start, he's using a RAM start. But if you go right-click at RAM start and say, find an open file. Okay, let me compile. This is the make or the build button. So now the color here changed. Okay, so go to declaration of RAM start. RAM start equates to 1000. So our RAM starts at address 1000 and ends at address 3FFF, hexadecimal. The RAM, the E², not the E², the flash memory, the program memory starts at 4000, okay, and ends at 7FFF. We can define another place as replacing the 4000 at C000, okay, and so on. So anyways, so every word here, blue color, you can go find this declaration in the include file, okay? But this is a number. Now, we didn't cover this yet. There are some words we're going to use, I'm going to cover it later. Even the instructions, we did not deal with instructions, enough instructions yet. We're going to do that later, but this is we're going to use very simple stuff to learn how to use this development environment. We're going to find instructions, just like load X. We know load X, right? We used it. It loads X with an operand. The operand in this case, the number sign says this is an immediate addressing mode, then a number 1, so X will become 1, okay? Store X, etc. And these are in dark blue, right? These are instructions. The light blue words are not instructions. These are either labels, like these ones. A label represents an address. So you want to say, like here, a branch to main loop, and here's main loop. So this is, instead of saying branch to address, and you go compute what is this address, you just main loop, and the assembler here will convert this main loop into a number. And you'll see when we build the executable, this will be replaced by a number. Okay, so the light blue are either labels or have an equivalent number if they're treated as an operand in the include files. Some, like the org, we say origin, or ds, define storage word in this case. This is all what I can see here. dr, origin, define constant, define storage. That's it. These are called directives. Okay, these are for the assembler to tell the assembler, when you go build your assembly program and create the executable, these are not instructions, just they are directives, commands given to this assembler running on my laptop, how to behave when it builds the program. But the result is not included in the executable that's going to run on the microcontroller. Okay, we're going to be able to differentiate between directives and instructions later on. But a short note, simple note, directives, you'll never find them in the data sheet, in the instruction set table. So equate is a directive. It's just telling it's just telling this assembler, wherever you see this ROM start word, just replace it with 4000 hex. Origin, it just tells the assembler, whatever comes after this line, and you're going to use memory, you start writing it at RAM start. And we just checked RAM start, it's address 1000. So when I reserve a data storage here, it's going to be reserved at address 1000. And this will be at, it's a word, so 1000, 1001, then the other one will be 1002, 1003. Okay, then comes the code section. We tell them start writing the code, because I'm starting to write code here at the ROM start. The ROM start is the flash memory in this case. Okay, so to start writing a program, simply go to the main loop, okay, and delete everything afterwards until you get here. Okay, I'm going to delete everything here. So here I write my main program. I'm going to explain what's before. And here at the RAM start, here I define this is my data area where I define the data. Okay. So here we do the data initializations, definitions. And then here at the main loop, we write our main program. Let's write a simple program to do what? And then before writing code, go plan for what you want to do. What do we want to do? Let's write a simple program that includes two numbers, مثلا number 1, num1, at address memory location in the RAM. I don't know, at the RAM start, whatever. What is the RAM start here? write the RAM start at address 1000, right? RAM start we saw. If you right click, go to declaration, RAM start is 1000. We can do to 2000, we can do whatever. Okay, fine. So at address 1000, sorry, undo 1000. And then let's have a number num2 at address 1001. Let's make them words. Okay, words. So num1 would be a word 16-bit, مثلا in hexadecimal 1, 2, 3, 4. And then here at address 1002 and 1003, we have another num2 that is مثلا 1122 مثلا hexadecimal. I want to add these numbers and store the result. So 16-bit plus 16-bit will be 16-bit, and store these results at a memory. I reserve 2 bytes for it to save the result. Oops, what is this? Okay. ماشي. num1, num2, sum. And we want this مثلا to be at address 2000 مثلا. Not any, I want to skip like 1000 places and go start at address 2000. Okay. So what we want to do is to store in sum num1 plus number2. Okay. 16-bit plus 16-bit, and the result will be 16-bit. Okay, so this is the plan. First, the numbers we're going to add. So we decided num1 is at address 1000, num2 is following, and both are words. So to reserve memory space, there are several ways. We're gonna look at all the ways how to book or to reserve memory space in the directives section, but a really easy way, num1, and in assembly we can write whatever. It's not case sensitive, so not like C. We can write whatever you want. I want to say define a constant dot word. What was our first word? $1, 2, 3, 4. Okay. So semicolon means anything following the semicolon is a comment. Okay, it's not going to be executed. So what we're doing here is we're putting in num1 the number hexadecimal 1, 2, 3, 4 directly. We're reserving this place, like you're saying integer num1 equals 1, 2, 3, 4 hexadecimal. And this will be stored right after this line. This line says anything after this line, you start it at RAM start, which is 1000. So this will be at 1000, but since it's a word, it cannot be placed in one location. It will be according to Big Endian. The 1, 2 will go to address 1000. The 3, 4 will go out to address 1001. Then num2 immediately follows it. Now, we're learning, okay? I can say another, again, define constant word and give it the word. But I can say define constant byte .b بدل word byte, and give it bytes with a comma separated by commas. The other byte was I want the highest byte, the 1 1, right? 1 1. I'm translating this into code. 1 1, then 2 2. Okay. 1 1, comma, $, 2 2. What we did here, we saved in num2 a word. Okay, that is $1122. So you can split it into bytes or just treat it as a single word. The difference is, say, define constant word or define constant byte. Right. Now what I want to do is to reserve a place for the sum. Okay, so I can say sum reserve memory byte. How many bytes I want to reserve? 2. Right. So here I reserved, I did not define a constant. Okay, I did not define a place. When you define, you have to place some a value in it, in that memory location. Here I don't want to put a value in the memory location. I just want to say I want to reserve 2 bytes and have this label pointing to them, sum. Okay, reserve memory byte. Now what's going to happen if I just keep it like that? The sum here, we semicolon. What we did here is we reserved 2 bytes at address what?
1005.
أول contain
Not yet.
num1 1000 and 1001. Then num2 1002 and 3. This
4.
comes at 4 and 5, right? At
Yes.
address 1004 and 1005, right? If I just keep it like that. But if I want to put it at address 2000, as we planned for our program in the beginning here, I want this at the sum at 2000. What I do is before this line, I say origin 2000, $2000. In this case, the sum will start, any memory location I start reserving here will start at 2000. So the 2 bytes I'm going to reserve here are going to change to 2000 and 2001. So far, so good?
Yes, Doctor. Yes.
Okay. Then we want to add, right? And then store the results. So now we're done with this section, the definition, the data definition section. Now I want to go and start writing my code. I start writing my code after origin ram start. Ram start is the flash memory. Okay, here, semicolon, flash program, and program flash memory start. Okay, and this is 4000 in this case. It can be 4000 or C000 hex. طيب, is this necessary? Well, it's not necessary, but you can keep it as initialization. This line means you're loading the stack pointer, load S is load stack pointer with an immediate number RAM end. Where does the RAM end? At 3FFF. صح? We saw it. 3FFFF, right? So what's going on here? I'm loading the stack pointer to 3FFFF plus 1, and this is immediate, which means what's going on here? So this is RAM. RAM here in our case starts at 1000 up to the last memory location $3FFF, right? So I'm going loading 3FFF plus 1. What is 3FF plus 1?
4,000.
4,000.
4,000. And 4,000 is what? Is the first place where our
Dash memory.
program memory starts, right? Program memory. Here is the data memory, the SRAM. طيب. What we're loading the stack pointer, load S with 3FFF plus 1 is you're loading the stack pointer with the number 4,000. So you're making the stack pointer point here. Stack pointer will point at address 4,000. So whenever you go push new data to the stack, we did not cover the stack yet. I'm sorry, but the concept should be there. It will start saving. The first place it would start saving at is where 3FFE, because every time you push, you go up. So the address decrements. ماشي? When you pull, you go down. So this is your stack. This means I'm defining my stack to start at memory location 3FF upwards. ماشي? This is the meaning of this line. So this is necessary to initialize where my stack pointer is at before I start using it. In this program particularly, we're not using it, but in the future we're going to use the stack. CLI clear the I flag in the CCR register, if you remember it. This is the maskable interrupt flag. When you clear it, you enable interrupts. Okay, we're not using interrupts. You can delete it if you don't want it, but it doesn't hurt to keep it here. These lines, the interrupt vector at the end, you don't touch it. Okay, you don't never ever touch it. But we're going to come to interrupt vector, reset vector. We're going to be adding to these lines. We're going to be adding to these lines later. But at this point of time, we have at address FFFE a word that says entry. Entry, what is entry? Entry is here, okay? What is this entry? Here, if you go compute, this is the RAM start. Any entry, I'm saying RAM start, and this is a label. So RAM start is the entry, okay? So address 4,000. This means when our reset vector, when we reset our microcontroller, or when a power on reset happens, the program counter should go point. It will fetch the address that it will point to from this memory location, FFE. This is called the interrupt vector. To go to FFFE, find an address, and point to it. In this case, we defined our address to be here at address 4,000. If I wanted to send it somewhere else, I just change this label, just move this label down here or whatever, or give a number. Okay. We'll look at these more when we look at the interrupt vector resets and interrupts. But what we want to do here is to start writing our program. So what do we want to do? We want to add, what we want to do is what?
Add number 1 to number 2.
We want to store in the sum the result of adding number 1 and number 2. How do we do that? And this is just an introduction into how to plan for our programs. How do we add numbers? We're adding words, okay? And we know this microcontroller is an accumulator base. So any one of the numbers we need to add should be put in an accumulator, register A or B or D. In this case, since this is 16-bit, we're going to load it to D. So the first thing we're going to do is, so I'm going to write my code here, load D with this number, okay? I can say address, I can just say num1, or I can just say 1,000. The assembler is smart enough to understand that num1 is 1,000, okay? Then I add D, which has num1 now, with num2. Okay, num2 or what? 1002. Then I store D at where? At sum. So a simple program. Is it clear? We didn't take the instructions yet, but 3 simple instructions. Load, bring the value at this location to register D, then add to it the value at this location, 1002. So we added the 2 numbers. The result will be stored at register D. So store D, which has the result of the addition, at memory location sum. Sum in this case is 2000. We can say, instead of sum, we can say $2000 equivalent. And you will see that these labels, num1, num2, sum, will be replaced with the numbers that we define them at. Okay, so I'm going to write my code. Load D with num1. Okay, so register D here will include, will get the number at memory location, what?
1000.
Well, إذا بدك more details, yeah, the higher byte will be 1000, $1000, and the lower byte will include the memory location. And I'm writing detailed comments for the first time. Okay, I'm not going to keep doing that later on, but just to make things, since it's the first program. Okay, so we're loading D with 1000 and 1001, which is number 1. Okay, then we're adding to D num2, and this will result in the result of this will add D plus the memory locations
1002
and 3. Exactly, which is number 2. You add it to D to itself, the result is stored over D, and it replaces it. Now D has the result, has the sum. I want to store this D, so store D where? At sum, simply. This doesn't need a comment. Okay, so sum at memory address 2000, well, with the $2000 and the lower byte 2001 will receive the what's in sum, sum.
What's in D, not sum, right?
Yeah, exactly. Yes, what's in D, sorry, which is the sum. Yep. Okay, what's next?
دكتور لو سمحت سؤال.
Yes, يزيد.
بقدر مثلا احكي لود دي اول شيء واحط الميموري لوكيشن، بعدين اجي اقول لود دي واحط مربع الرقم اللي بدي اسيبه فيها.
what you're saying is here.
يعني بدل ما اعرف نمبر 1 نمبر 2.
This is saying load D with the memory location, give it the address directly.
مثلا $1000.
Okay, you don't want to say num1 here.
Number 1,
you want to delete this label. You don't want this label. You just say define constant word.
وبعديها اجي اقول لود دي واحط مربع واحط اللي جواته اللي هي 1 2 3.
You don't need مربع. You just say 1000.
هاي اول وحده. بعدين ثاني شيء باجي بحكي له لود دي مربع بالشيء اللي جواته، صح؟
1001 you mean؟
لا هسه بعديها الامر اللي بعديه لود دي.
You add. Now you want to add.
ايوه.
Load add D. Yes. With address 1000 1002.
لا ما كان هيك قصدي. هسه دكتور مش إحنا
دكتور
لما نحكي
هو
لود
قصد يزيد.
Yes, tell me.
انا فهمت قصد يزيد بحكي انه ما بده يحط هذا اول اشي عملناه انه دغري انه لود الدولار
numbers.
ساين 1000 هدول انه clear this.
Remove these.
بالضبط.
يعني
بده يحط بعدين ستور انه ستور دي بالهاشتاج انه النمبر بدنا اياه.
Okay, you want to load D.
تمام بالدولار ساين 1000.
Immediate.
لا دكتور
Dollar sign 1 2 3 4.
هاي قبليها بده يكون لود دي 1000 عشان يعرف لي انه اللوكيشن تبع دي 1000.
Okay. Then you add 1 1 2 2.
ايوه بالضبط. بعدين اقول لود دي بالضبط. تزبط
1 1 2 2. Yes, of course. But in this case, يعني the result is going to be the same. You're adding an immediate number. Now this 1122 here is not an address. It is the operand that you want to add to D. Okay.
ايوه بالضبط. بس هاي دكتور بدها تكون ال دي.
But this is يعني you made it like a constant. يعني just like when you go in C, you say x plus 3. It's good. You cannot change. It's part of the code, right? It's not like x plus y where you can change the value of x and y.
دكتور
Here it's a constant.
انه دي صار مثلا الميموري تبعه 1000 و1001. بعدين اجيت انا حكيت له لود دي بالرقم هذا اللي هو 1122.
Yeah, you can do that immediately. Yes. But you know, you got limited that this is a constant. You cannot change it unless you change the code. So,
مظبوط.
yeah. Yes, you can do that. As the result, a final result, numerical result, adding the numbers, the result is going to be the same. Okay. So allow me just to remove these things to keep a clean program. Mashi, we're done. Are we done? If you compile here, this button, make, build, this builds the machine code. Oops, we got an error. What is not HC12 instruction or directive? This is another error, num2. Okay, what else do we have here? Not HCS12 instruction or directive, compile failed. I believe, let me just check this thing. طيب. This is okay. Can I just make it a small letter and check sometimes? Just to make sure. num1. Okay. طيب. Another thing. You may need to start at column 0 just to make sure. Yes, شايفين? The error I got because I had this tab or spaces before it. ماشي؟ فهمتوا شو الإيرور؟
يس دكتور.
Yes. شوف راحوا. This error is because that I replaced the num with small letter. Thank you. Yes. So I can bring them back to capital. خلاص.
يعني مش case sensitive بس عشان احنا
لا مش case. Well, the label is case sensitive. I'm talking about the code, the instructions. يعني load D, define, these instructions in dark blue are not case sensitive. But labels are, I think they are. Yes, they are. Labels are. Now we don't have any errors. Okay. What's missing, guys? Tell me.
Showing the result?
Well, the result is here. How to see it? Well, you listen. When we run now, we can see it by simulation. We're going to look at the register, the memory location, we're going to find it. Now, to see it on this microcontroller, we either need a display or show it digit by digit on the 7 segment. We need a way to display. It's not our problem now. We're going to come to ways later how to display numbers or use them. The result is not to display. The goal is not to, it's not the display thing. Now, what I'm asking about is the program here. Do you feel anything is missing?
ننهي البرنامج دكتور.
ننهي البرنامج يعني كيف؟
finish أو
أو end مثلا
او end. Yes.
أو end. طيب end is called a directive again, just like the org, the origin, just like the define constant byte and constant word. And this directive means that you're telling this assembler, the CodeWarrior assembler, whenever you go build the machine code, convert these instructions into their machine code. When anything after here, مثلا لو هون, if I have a load x with an immediate number 1, this instruction is not going to be counted. It's going to ignore it. It's not going to convert it to the machine code. Okay, this is the meaning of the end. So I can just remove the end. I don't need it. No, what I'm talking about is something else. Let me ask you a question. When you took your programming class, first programming class, you used to, most of you took a C programming class. You used to use Visual Studio or whatever, right, to write your program. When you used to reach the end of the program, you return a value or whatever, right? Then what happens? When your program ends running on the laptop, what happens? It closes, right? And you go back to Windows. Is my question clear? Now, this program we're writing here is going to be run on this microcontroller. There is no Windows. There is no Windows. But there is a program counter. The program counter, as long as it's receiving a clock pulse from the oscillator and there is power, is going to keep incrementing and pointing to the next instruction to be executing. Nothing is going to stop it. Okay?
Return, دكتور, مثلا.
Return what? Okay, thank you. I like your answer. Return. You return to another piece of code, right? So in Windows, when you go run a piece of code, when you're done, you go back to the code that is running Windows, right? You return where? Return means go make the program counter to, you're done with this piece of code, go point to another piece of code. The other piece of code could be just display these graphics I see on my screen.
ممكن دكتور ريست للبروجرام كاونتر.
Reset, يعني go back and re-execute it. That could be something. يعني what does reset mean in this case? A reset means that the program counter will go back here.
Yes.
Right, and redo the thing again. What I want to say, that as long as in embedded systems, in microcontrollers, the program counter is going to keep incrementing, pointing to next instructions, fetching instructions, executing instructions. You shouldn't run out of instructions, okay? And if this microcontroller is controlling the engine in your car, or controlling the climate in your room, or controlling whatever, you don't stop it, right? There is nothing to end. It has to be running, keep running forever, right? So in embedded systems, we always should have an infinite loop, doing something over and over again. Read the sensor, convert the reading into a physical meaning representing temperature, check if the temperature is above or greater than the value I read from the remote control, decide to turn on the compressor or turn off the compressor, then do what? You go check it again, check the temperature. Did I reach my set point? Didn't I? Okay, and keep doing something forever. Okay, you cannot just go disconnect your controller and you're done. So in any embedded system, we should have an infinite loop. Okay, in this case, I don't see a reason to keep doing loading D with num1 and adding it and storing it. Okay, I can say here branch just any jump, they can jump, or go to for those who dealt with other controllers. branch to main loop. This will make the program counter, when done here, instead of continuing downwards, is to go back to here. Well, I don't want to keep doing this, so I can do another one forever, مثلا forever, and create a new label here, call it forever. Forever. This will tell the program counter, branch here, branch here, branch here, okay? So get stuck here. Make the PC program counter get stuck here. If you don't make it get stuck here, it's going to continue. Yani, for example, if we want to draw our program memory map, what will be in the program memory? The first location is address 4000, right? We will have the machine code for this instruction. We said the size of an instruction, you can get it from the data sheet. Then this instruction, then this instruction, then this instruction. Let's say 10 memory locations. But there is memory locations afterwards, right? And this is flash memory. So you can probably have all the instructions from the past. The program counter will continue and go fetch things from those locations. Okay, and you don't want to have that to happen. Okay, you want to go into a loop infinitely where you wrote the code for it and you know it. So this infinite loop is necessary to end our program. Okay, build, no compilation. Yes.
هلا إذا حطينا بعد البرانش إنه نيو كود، هل هو رح ينفذه ولا بيعمل عمل الإند؟
Okay, لو كتبت هون load x number 1, what's going to happen? There are two passes, Mariana. Yani, the first pass is for the assembler to convert every line of code here into a machine code. So, short answer, the assembler will convert this load x to machine code. It will put it in program memory location right after the branch. But when you go to actual execution, the program counter will get stuck in this infinite loop. It will never go to the load x. So the load x will never get executed. Okay? Yani, if I have an end here, load x will never get to convert it to machine code. It will never be stored in the program memory. Mashi? So nothing in the program memory. No load x. It doesn't exist. But with no end, no, the assembler will generate the machine code for this instruction, put it in program memory, but in actual execution, the program counter will never get here and fetch this instruction. Is that clear?
تمام.
Okay. Right. So we built a program. Let's run it. When we want to run debug, this will run this green arrow. The same, you can make them here, but the build, make is the build, and run. I don't know. I know this is a green arrow. Mashi. What do you pick from here? In this case, right now, we're going to use full chip simulation. Later on, when we download to the hardware, we're going to use something called serial monitor. For now, let's simulate. Hit the green arrow. This is the thing you get. And what do we have here? Here is our source code in this window. Source, it says source. So the first line, this is our source code. It included, of course, all the includes, right? It becomes a part of our source code. Mashi. So this is our source code. Okay. Where do we go? Here. This is the source code. Our program starts here. The memory locations we reserved for data in the RAM are here. So num1, see, it defined it as an integer 4660. What is 4660? What did we put there in the original? We put a 1223 hex, right? So if we go to the this 4660, if you right click and you say I want to see the format in hex, this is the 1234. But we just saw it in decimal. So num1 is 1234. Num2, but num1 we said define constant word, right? We booked a word, only one word. Here is it. It's an integer. While num2 we booked 2 bytes. A byte is an unsigned character. Remember that when we go back to when we're going to use C. An unsigned character is an 8-bit number. So the first 8-bit number is 11. The second 8-bit number is 22. 0x means hexadecimal, right? Hexadecimal, equivalent to the $sign.
هون بالسي هذا صح؟
Yeah. Well, and everybody almost uses 0x, but in this assembly, it's a $sign. Okay. See, we're going to use it as a, we're going to, in our code, we know that we said add num2, and we treated this as a word. But when we booked it as 2 separate bytes. Then the sum, here's the sum. We booked 2 memory locations, and they are undefined yet. For the ones we said define constant byte or define constant word, we gave them what's the number inside. For the reserve memory byte, we just booked or bytes, and we didn't save anything in it. Okay.
دكتور بصير سؤال.
Yes, Shadi.
هون بالundefined unsigned character، طب هو ايش فعليا بيكون جوا الميموري، ولا يعني doesn't matter اذا كان في قيمه ولا ما في قيمه اصلا؟
Sometimes you'll see it. Wallahi, sometimes I forgot to initialize something. If you do, if it's non-volatile memory, you'll have what you had before. If it's volatile, some assemblers, some compilers, when they program, go initiate the values. But it could be something rubbish, right? If a piece of RAM, you disconnected power from it, it could flush, it could have zeros and ones are voltage levels, So undefined, you don't know. Okay, they will become defined after we use them. They're in RAM. And this is expected from RAM. We did not reserve them in any non-volatile memory. Okay, so this piece shows us our data memory in a friendly way. Okay, but we're going to see them in the actual memory here in the memory map. But what else do we see? The assembly here, this window, the assembly. Okay, 4000 LDS 163. Okay, let me convert things to format here to hexadecimal again. Load S 4000 اللي هي ايش؟ اللي هي كانت load S with RAM end +1 هاي and we computed it 4000 at where? At address 4000 program memory اللي RAM start. Then and CC condition code register with EF. EF, you're ending everything with 1 1 1 0 1 1 1 1. So you're ending everything with ones except for 1 bit. You're ending it with 0, which is the I bit. You're clearing it. See, this is the result of converting the CLI into machine code. Okay, this is the assembly instruction. So here in this step, the machine code, the assembly code we wrote here is converted, is still assembly code, but it shows us in this column, the real program memory address that this instruction is going to be stored at, its size, and remove all labels. So you're not going to see num1 here. So in here, we said load num1, right? You see my mouse?
Yes, Doctor.
Yes.
Okay. Load, and on the left, load D with num1, but on the right, you say load D with 1000. So the assembler removed all these labels we used here and replaced them with the actual numbers. Okay. So load 1000 اللي هي number 1, and this instruction load is stored at program memory 4005, 6, 7. So it is a 3-byte instruction. Do you want to make sure? You want to go check that? You go.
2 بايت.
It's 3 bytes instruction. So if you go check the machine code for the load, let's go check it real quick. Where is let's check it real quick in the CPU, in the resources here on the left, resources. This one is easier. Okay, let me Control F, load D. Load D, load D, here's the load D, and we gave it an address, right? And the address was a 16-bit address. So it's an extended addressing mode. So see, your machine code, the object code is FCHHLL, high, low, FC. So FC 1, 2, 3, 4. Okay, so 3 memory locations. 3 memory locations. Where's CodeWarrior? Here. Okay. Yeah, where's the simulation? Here. Mashi. So load D. Oh, okay. It's 1000. Now one. Okay. 3 memory locations. Store that address 4005, 4006, 4007. So this is the 3 memory. The add D will start right after at 4008, and its size is 8, 9, 8. Also 3 memory locations. Then comes the store at 2000. Then the branch here. Okay. The absolute value here calculated is 400E. Okay. So I'm telling the program counter, branch to 400E, branch to 400E, and it continues. Okay. Here we have, see, some instructions from before. Maybe this is the default. Store A, accumulator A at address 5A. All other locations. Mashi. But there is memory, and it includes something. It includes something. You don't want to take the risk, okay, and make your Wallah, shuf hada. Did we ever write this code? Maybe this is from all time. I don't know. Load S, load H, subtract. And you may find things in the program memory. You don't want to lose control of your program counter. Your program counter should be under full control by you. Okay, by you. We were at address 4000. How should I go back to address 4000? Here. 4000. Is there go to set address 4000? Yes. Okay. Here. So this is our assembly program generated by the assembler. Right. So I'm still showing you around. Okay, we did not run the program yet. Here is the registers window. So the CPU registers, cycle 0, we still didn't run. D is the D register. This is the default value, maybe CB. And D, we know that the upper part of it is A and the lower part of it is B. Index register X, index register Y, instruction pointer, or you can call it program counter. This is going to be the same, Mashi? Program counter or instruction pointer. Program page 0, we said that the 256 kilo flash memory can be addressed through a 64 kilo byte window. Through 16-bit addresses can address 2 to the 16, which is 16 kilo. Okay, but we have 256, so they're divided into pages. How do we move from a page to a page? There is a register called P page. Okay, stack pointer value, CCR register. See, this is the I bit. Here are the carry flag, the overflow flag, the 0 flag, the negative flag, the I flag, the interrupts flags, and so on. ماشي؟ طيب. And finally, this is the memory. This is the memory. The memory address space, the full memory address space. So here I can say, okay, go to address 1000 hex. It will take me where? See what you find here?
Num
1, 2, 3, 4. هذول the first linum 1, 1, 2, 3, 4. Then 1, 1, 2, 2, linum 2. Then undefined, undefined, undefined. Okay, so this is how you read the memory. So the first column is 1000. This is the 1001, 1002, 1003, 1004, 5, 6, 7. Then 1008. So every 8 locations in a row. Then 1008, 1009, 1008, B, C, D, E, F. Then 1010. And so on. Okay. This part over here, if the number here is equivalent to an ASCII code, you see the equivalent character that is represented by ASCII code. We know that ASCII characters, 30, you add any number plus 30, you convert. So 34 here is shown as a 4. See? A 22 doesn't represent a number, or maybe I do SL codes. طيب, let's go to address 4000. 4000, where the program is. Okay, here's our machine code. So address 4000, you have a CF 400010. هاي هي ايش هاي؟ load S with 4000. يعني if I give you this, يعني if I take a screenshot from here and ask you in a quiz or in an exam or whatever to give me the equivalent assembly code, you should be able to. You go, oh, what is CF? CF, let's go check it in the instruction set. CF, you go to the instruction set.
هذا دكتور بيكون الماشين كود صح هيك؟
This is the machine code, yes. You go search in the instruction set for CF. Here, Control F, CF. شايف؟ CF معناتها load S. Load S. CF then JJKK. JJKK بكون تعريفهم فوق اللي هم يعني lower byte وال higher byte من address you're loading to S. So it is a load S instruction. Load S instruction 4000. This is load S 4000 hexadecimal. Then, okay, this is the first instruction, 3 memory locations. Then 10 EF, where do I end? I need to check the 10. What is the instruction that starts with 10? I go check the instruction set table, and then you'll know what's following. ماشي. But we at least we just checked at 4005 the load D starts with F3 صح? With F3 or FC, sorry, FC, we just checked it. And if you go back in the recording, you see FC 1000. So this is load D with 1000, 3 memory locations. Then add will be F3 1002 اللي هي هذه 1002, and so on. Okay, this is our machine code. So this space over here is the memory space, including data, stack, program, whatever. Okay, I just want to run يعني the program. Go يعني we still have like 6 minutes to finish this, to close the topic. So we're good. Okay, everything here is clear.
بس دكتور الريزلت اللي انا بدي اخزنها ب 2000 كيف بشوفه هون؟ ولا لسه انا ما عندي؟
You can say here address, go to address 2000. Let's see it. Right now there is nothing. We did not run the program, Mustafa, yet. Remember, we didn't run it. So this address is 2000, nothing in it. Also some here, still nothing in it. Now I want to run my program. I can either just hit this start button, the green arrow, you see my mouse, and it will run. It will run, you'll get the result. or if I want to go a step by step, I can single step here. ماشي, single step F11. A single step will make the program counter move instruction by instruction, instruction by instruction. Okay, let's do this. And here are the registers. Now the program counter is pointing at 4000. يعني كأنك توك عملت reset. You just powered up. Okay, I click the single step button. Now the first instruction, load as, fetched, decoded, and started to be executed. The program counter immediately points to the next instruction, 4003. See, هذا الأحمر means this got modified. Program counter is pointing now at 4003. Remember, program counter always points to the next instruction to be executed. So where the program counter is pointing is not the one being executed. This is what's gonna come next. ماشي. Stack pointer, we made it point at 4000. ماشي. What happened there? What else happened? So we're here, program counter. We're running at 2 megahertz. This is cycle 2. Single step مرة ثانية. Okay, single step. شوف on the left here, I think this is highlighting the instruction we're running, and on here in the assembly. Now load D with 1000. Load D with 1000. It's not executed yet. The program counter is pointing at it. شوف and condition code register with EF يعني is gonna clear I bit. See I bit هون صار فاهي يعني became not black, gray, cleared. Okay, afterwards the load address 1000, contents of address 1000 اللي هي 1234 to D register. D register right now it's at its default. After I run, it's gonna load, and the program counter is gonna point to the next instruction, to 4008. Let's check it. Single step. Now D يعني load address 1000 اللي فيها 1234 executed. So D is 1234, A is 12, and B is 34. Stack program counter moved to the next instruction, 4008. So we loaded D. Now D has the first operand. Now the add is going to execute, and the program counter is going to go point to the store. Single step. Add 1234 plus 1122 hex. This is what you get, 2356. If you want to check it using the calculator, the programmer calculator, hexadecimal, 1234 plus what? 1122 is what? Equals 2356. 2356 is what we got, right? 2356. So the result of adding the two numbers is stored in D. The program counter is now pointing at the store D 400B. ماشي. The addition resulted, add should impact the carry flag, zero flag, everything. These are the flags, you can watch them. And we're at cycle 9. Okay, instruction cycle 9. طيب, single step again. Store is saved now, is executed. Program counter points to 400E. The store 2356 is stored to address 2000. Go check address 2000, ya Mustafa, in the bottom. 2356. Stored. See it?
Yes.
Yes. And in the left, at the sum, you see it as well. 2356. Tamam? Now, if you keep clicking single step forever, all what's going on is this number in the bottom here is incrementing. The cycles. The program counter is always pointing at the same. We got stuck in an infinite loop. خلاص? Okay. So if I want to reset, I can hit this button with the red circle. Reset. It goes back to the default as if we just did a reset and made the program counter point back to the first instruction. See, that the values in the registers and memory locations did not change. See, that's why it is important دائما انك to initialize your values. Don't rely on what that this could be when you make an integer x that by default is going to be 0 or whatever. Don't assume that. Actually, now I'm going to hit the green button. Everything is going to happen in a few cycles and we get stuck in the infinite loop. Now the program is running forever. See, and now we are 60, 80, 90 something million cycles. See, we're moving very fast. CPU cycles. Is this clear? I can halt at any time, stop the program execution. I can reset. Using this simulation tool, is it clear?
Yes.
Yes.
Next time I'm gonna download the same program on this microcontroller, okay? And run it here. 6:15 already, 6:16 we took 1 minute extra. I'm sorry for that. But I hope it took an hour and 15 minutes, but I hope it helped break the ice with this development environment and we can start easily using it. We'll go more into later on with more deeper and complicated embedded software design, but the goal of this lecture was to be able to use this tool. If you have any questions, you can stay. I'm going to stop the recording and we can chat afterwards. Thank you very much and see you next time.